Good afternoon, everyone. My name is Yan Ji. I'm from Georgia Tech. Today, I'm going to talk about our work on refinable attack investigation in the setting of multi-host. So nowadays, there are more and more attacks that involve multiple hosts. For example, in 2015, the Taiwan First Bank suffered from an attack that steals the money from their ATM machines, which involves lateral movement of multiple hosts. And also that in the Kubernetes threats, attackers used persistent and lateral movements also to infiltrate the financial institutes. And also that interestingly, in the Black Hat of last year, 2017, researchers from NCC group proposed the Git point, which uses not only the Git client side, but also the Git server side to exfiltrate the data from the client side through the server side, and then finally get to the attacker side. So after that the attack happens, so our goal is to investigate these attacks with the goals of accuracy, efficiency, and of course supporting multiple hosts in this background. So this work focuses on the challenges when we achieve these goals and our corresponding approaches. So first, let's see a high-level example of the cross-host attack. So the attacker tries to exfiltrate some sensitive data from the client side through the server side and finally to the attacker side. He scans the file system of at the client side, and he selectively pick like file A, and then to send it through the server side, and then to the attacker side. So during the investigation, so people may ask questions like, what data were leaked exactly to the attacker? Was file B leaked or was file A? If we know that it's file A that is leaked, so how was file A leaked step in step? So what's the nature of this attack? So in order to answer these questions, so we need to first to tell that exactly file A has been leaked, not with the false results like file B or C is actually leaked, and also that we need to find out what's the data dependencies between these multiple hosts, so that we can analyze them step by step. So this challenge is aggregated when we turn to a peer-to-peer network setting. So we need to find out like only these hosts have been involved in the attack, not the remaining ones. So the question is that do we have to serialize these convoluted data dependencies between these multiple hosts? Can we instead apply the analysis in parallel and aggregate the results after we complete these analysis which has been done in parallel? So when we analyze these data flows across different hosts, so we find it's challenging. So we summarize these challenges in here. So first, that it has the false positive dependencies, like in the previous example. So we need to tell that actually only file A has been leaked, not the file B or C, and also that the data dependencies across these multiple hosts should be tracked correctly in the analysis. And also that because we are not only dealing with one single host, but multiple hosts, so the analysis cost including the analysis time and the memory cost is amplified. So how can we give a reasonable analysis cost? So we solved the false positive dependency, our first challenge, by using dynamic taint analysis, which has been known to be able to dynamically instrument the program at instruction level, instruction by instruction, so that it can tell exactly the exact data flow. There are mainly two categories of taint analysis used in the that has been presented. The first category, like the cloud fence or the taint exchange, they focus on using the taint analysis directly in the runtime of the program, and then they can track the accurate dependency from one host to the other. However, since the taint analysis, as we know, is very expensive, so they suffer from the very high overhead, which can be over 10 times or to 30 times higher. So and the second category is called refinable attack investigation, which uses recurrent replay technique to decouple the expensive dynamic instrumentation of the taint analysis from the runtime of the program, and then we record this program with a very low overhead, and then at the replay time, so we do this expensive taint analysis. So it can achieve both efficiency and fine-grain the level of the analysis and also accuracy. So mainly there are work like R0 and RAIN. So first we do a system-wide recurrent replay, and then we prune this data according to the target of our analysis of our attack investigation, and finally we selectively replay the execution with the taint analysis. So we have chosen to solve this one with the refinable attack investigation way, and there are two remaining challenges. So the first one is that we still need to fulfill the same data dependency that happened in the recording time. So we need to add the replay time so that we can accurately track the data dependency and find out what is really going on and what the data flow is. So we are trying to enable attack dependency free and independent and parallel replay so that we can do the taint analysis without serializing the replayed executions. And also that we aim to optimize the analysis time, because if we do the analysis in parallel, so we can reduce the analysis time cost, and also further that we aim to reduce the analysis memory cost. So our approach is to, as I said, to enable the independent and parallel replay the DIFT. And we reduce the memory cost of DIFT by optimally allocating the tag size for each DIFT task. So here that during the selective replay of each execution, so our system called RTAG facilitates the tagging that is needed during the taint analysis, so that no serialization is needed, so that each replay can be done independently and in parallel. So this is the overview of our system. It is composed of 4 parts. So first, that we have a tag association part that tracks the data transmission between different hosts, and we use a tag and our tag allocation optimally calculates the tag size that is minimally needed in every DIFT task, and we use a tag switch technique to allocate a locally symbolized tag for each DIFT task, and then finally our tag overlay is going to aggregate these results and then return the final result of the analysis. So here that we use part of the git pull attack to show how our tag works to facilitate these tagging. So here that on the left side, for example, the attacker aims to exfiltrate the SSH key through the git pag command, and then it crosses this from the client side to the server side through the SCP, and then finally the server side hook is going to read from these temporary object files from the SCP, and finally it's going to generate an archived file. So these are the system call level data flow that we can see. So our target is to find out how does the SSH key goes to from the client side goes to the archived file on the server side. So when we are doing this analysis, so first that we need to identify every byte that we need to track. So in this data flow analysis, for example, here that the SSH key needs a global tag, which consists of like the host MAC address, the inode, dev, gen information, and its offset, and also its version information. So totally, it's 208 bits. So can we just use this global tag, which can make every tag identifiable across different hosts in the taint analysis? Obviously, it is very high. So our approach is to first analyze this syscall trace, and then to allocate an optimal tag by using the result of the syscall trace analysis. So, for example, here that if there's a read syscall with the 6 bytes of data read to the memory space of the git pag process, and then there's a write syscall which writes to the object file. So if our target is to track these data flow, so here that instead of using the 208 bits, so we only need 3 bits to identify these the sources of this data flow tracking. So we compare the text sizes of our scheme with the previous systems. So as we can see that as the number of the symbols for each DIFT task grows, so our RTAG, local tag, grows in the log scale. However, the others is one is from the Titan. It is so it grows exponentially, and also this the D tracker and our global tag is also much higher, and also that the memory cost for the according to the number of the tags that has been used in the memory space, also our local tag is a fraction of the other compared with the other systems. So, and next, when we have our symbolized local tag, so when we do the DIFT at the I/O syscall, like read, write, receive, and send syscalls, so we shift our tags from the global scope to the local scope, and then we perform the taint analysis, and then when we get the results, so we shift them back. And then we update our global tag map. So still that we need to link the tag propagation between the two hosts via the socket communication. So currently we support both the TCP and the UDP packets with the tag, with this tag association, but in different ways. So in the TCP, that because it preserves the order of the data stream, so we use a counter-based approach, and for the UDP, we use a tag embedding based approach, because there can be data losses that the tag propagation can be lost. So for the TCP, the data stream at the sender and the receiver can be not aligned. So they can span over different numbers of syscalls. For example, here that there are 3 send syscalls and sending these totally these 15 bytes of data. And at the receiving side, there are 4 reads. So our approach is to track the data stream in one TCP socket session so that we can know which has been sent and which has been received accordingly. So for the UDP case, that because it's datagram transmission, so we use the tag embedding approach. So we implement the tag embedding routine in the internal socket handling stack before the checksum has been computed, and at the receiving side is before the checksum has been verified. So here that when we compute the data flow in each DIFT task, so we combine these results into our tag overlay on top of the classical provenance graph, and then we get the final result. So here, this example, our running example gets the result for each data flow in each DIFT task. It's from, for example, from the file A. There are 2 versions consecutively from the 2 temporary files B and C, and then further that we can backtrack till its original file E, which is our SSH key. Okay, so we have implemented our RTAG system, and currently it runs both on the Ubuntu 12.04 32-bit and 64-bit, and we use libDFT as the DIFT propagation engine. Also, it supports 32-bit and 64-bit propagation, and it uses Neo4j for the graph-based reachability analysis, and we use PostgreSQL for the tag storage. So in the evaluation, so we focus on 3 aspects: the effectiveness, the analysis overhead, and our runtime overhead. So along with the Git pull running example, we also evaluated in the different settings, including the server and client setting with the Firefox browser at the client side and the Apache server at the server side, with 2 SQL injection cases. And we also have the CSIF case also in the server and client setting, and the one cross-site scripting. And also that we use a peer-to-peer case with 6 hosts, and we use the Nutella peer-to-peer file sharing protocol to evaluate our system. So when we do these queries, so we find that we can accurately recover the exact data flow across these different hosts. And this is our analysis time reduction compared with the other cases when the analysis is all serialized. So it can reach up to 90% of the reduction. And the runtime overhead, so we run the SPEC CPU2006 benchmark, and the mean of the runtime overhead is less than 5%. And we also reduced the memory cost compared with the previous system, including Dighton and dtracker, with 50 to 99%. And actually, that there are 2 cases that Dighton could not complete in the Firefox and Apache case. And also, we evaluated the impact to our network performance, including the bandwidth and the RTT. So for the bandwidth, we have less than 0.5% of the reduction. And for the RTT, our impact is less than 0.05%. So in conclusion, our RTAG enables the cross-host refinable attack investigation, and it decouples the tag dependency from the replayed DIFT, so they can be put in parallel and independently. And also it improves the memory cost in the synchronization. So the runtime overhead is less than 5%, and it hugely reduces the analysis time cost and the memory cost. So this concludes my talk, and I welcome any question. Thank you.
Do we have any questions? One question that I had, in the case of the UDP where you're embedding tags in the packets, what's to prevent an attacker sitting on the network stripping those tags away so that you can't do the tracking anymore?
So our current threat model is that we don't assume that the attacker can compromise the kernel, and if the attacker compromises other packets on the run, currently we don't cover this part, but I think it can be done through the adding some of the hash and the verification scheme. Yeah.
Okay. Any other questions? If not, let's thank the speaker one more time.